Okay. Okay. So let me start by saying that I am honored that I can speak here. I love South Africa. Anyone who has been there love the country, and in particular, Cape Town is such a fantastic setting there. And well, congratulations to all of you in South Africa. I'm here in Dallas, Texas, which is extremely boring. As you know, United States people do not socialize much, and I do not know even my neighbors. So you go to the streets, there is nobody in the streets. So it's kind of different kind of life. I would be honest with you, I prefer the kind of life you have in South Africa. Congratulations to all of you. I will talk about this topic, Pygmy resonances, neutron schemes, and neutron stars. I was drawn to this situation of talking about something related to neutron stars because of my friends, experimentalists. I like to work with experimentalists, and nowadays in nuclear physics, it's very difficult to do anything without relating our work to neutron stars. Not only neutron stars, but supernovae or whatever happens in the stars or in the universe. I think there is still some of our colleagues who are doing nuclear physics for the sake of understanding nuclear physics, but most of us nowadays, at least in our papers, we put a paragraph writing something related to the stars. So it looks like it's the main motivation for nuclear physics. And it's not different for me. So I was drawn to this. So I will show you some results that I was involved with, but mostly in collaboration with my colleagues, my former advisor, Gerhard, a colleague I still keep contact. He's now a dean, Andrew Sustich, Sagawa-san. We did lots of things together. Thomas Alma is an experimentalist in Darmstadt. Mahi Hussein, he passed away last year. Stefan Tipo, who is very active, he works also at GSI, as well as Peter von Mancuso, has done several experiments in ITEMA labs. Oro Bugek, who is a theorist and works in Seattle. And then I have some students and postdocs in Commerce, where I work, Texas A&M University Commerce. Paulo Avogadro, Shub Shintak, Honyang Liu, and Ronaldo, they have worked on this subject with me. This was a student, Jocelyn, Michael Hartos, James Thomas, and Nathan Brady. They all have contributed to what I will talk about. So the subject I'll talk will be mostly related to my work and what I have contributed to it. So I will apologize if I do not cite some important names in the field. I will try to be fair to everybody, but there are limitations in time. So
Carlos,
if I look for...
Carlos, can I interrupt you? Can you put full screen, please?
I have full screen. You can't see it?
No, we still see a lot of the sidebars.
Oh, you see a lot of sidebars. Let me do one thing. Let me pull out the PPT and see if I can do better with it. Okay, just 1 second. Let me see here.
It's possibly that the window's been selected to be on the PDF viewer for the slides, not on the full screen display.
Oh, I see. Okay, so I'll try to get out here. Oops. And try to move to the other screen. So let me see now. Can you see anything? No?
Not yet.
How about now? No?
Mm-mm.
Okay, then I have to get out again. I'm sorry, guys.
No, don't worry. Don't worry.
By the way, I see that Bjorn Jonsson is there. We had a meeting, right, Bjorn, a few hours back. It was 2 in the morning for me here. How about this now?
It's over. The meeting is over.
Yeah, I know the meeting is over. I went to bed for 2 hours, and now
Yeah,
I'm.
but it ended in time, so I could.
So can you see that, Xavier?
No, no, now it's not working. So maybe you just stop sharing and then share again, maybe.
Okay, so it had to happen with me, right? Okay, so where I stop sharing and share again.
Yeah.
Okay. I share screen now, and I go to the PPT. What about that?
Okay. Now we can see the
Full
cannot
screen. And what happens when I put full screen?
That's better, I would say.
Is it?
Yeah.
I'll
Yeah.
try this way, okay? If there is any problem, you don't see me, you don't see it well, let me know. Well, okay, so neutron stars, this is a collection of things that we see around about neutron stars. They were proposed in 1934 by a guy here in Texas, Zwicky, and also by other people like Landau. And we think that they are remnant of supernova explosions, stars which have masses which are beyond 8 solar masses. And we think there are like 100 million of them in the galaxy. We really don't know. I think these are just estimates. Their masses could run from 1.5 to 3 solar masses. And we think that if they are larger than 3 solar masses, they collect a black hole. It looks to me that from recent publications, the largest observed neutron star masses are of the order of 2 solar masses. So due to angular momentum conservation in a supernova collapse or in a neutron star merger, not in a neutron star merger, but in a supernova collapse, the neutron stars, they rotate and they have a period of milliseconds to seconds. The densities are enormous. Okay, we cannot understand these numbers in astrophysics. They are too large. But if you put the matter of a neutron star in a matchbox, it would weigh more than 10,000 Empire States Building. That's something that perhaps we can understand, but it's still unimaginable. The radius is about 10 kilometers and the surface temperature about 1,000,000 degrees Kelvin, and this allows for X-rays emission. And the pressure at the center, we think, is about this number there, 10 to 34 pascals, which is something unimaginable. The magnetic field is also very large. It's so large in Teslas, 10 to 11 Teslas, that it can even produce pairs due to vacuum polarization. And the amount of energy stored in the crust of neutron stars and the fracture of it could lead to soft gamma ray emissions. The acceleration of gravity at the surface is enormous. It would lead to spaghettification of a person falling to it. The gravitational binding is about 100 MeV per particle, which is much more than what we have in usual nuclear physics. And what we are being able to do with the TOF equation is to relate masses and radii, and there are some uncertainty, and all this uncertainty comes with the equation of states I'll talk about. As you know, neutron stars were observed also as pulsars by Jocelyn Bell in 1967, and she came to Commerce, and I'll talk about this a little bit later. This is the cartoon that you probably have seen. I took this from Nature, where you have the neutron stars, the outer crust, the inner crust. I think, in fact, this part here is the most interesting part, the crust of neutron stars, because of the structures it has and so many things that one can study here. But it has also a bulk, and the bulk has some sort of liquid, superfluids, and of neutrons, and we don't really know what happens in the center of neutron stars, and there are lots of both. At this stage, I would like to say that many of my colleagues, they love to work with neutron stars. Many theorists, they apparently are drawn by the fascination with neutron stars, but also with the fact that it's much easier to develop some sort of theory for neutron stars than some sort of theory to explain some experimental data, which we have on Earth. So when Jocelyn Bell came to Commerce in 2010, here's a picture I have with her. I proposed that we would edit a book, and I contacted Jorge Picarevics, and we produced this book here. I think in the end we published it in 2013. And Jocelyn was very nice. She wrote a preface to our book, and in fact, it's not our book; it's the book of all who have contributed, including our chair. And so that's how I was drawn to this physics. And then I'll talk a lot about Pygmy resonances. And this is the timeline, the history of how it was first observed in 1961 with gamma rays from neutron capture. This is the reference. The first time, apparently, the name was used was in this publication in the Canadian Journal of Physics in '69. Okay, and then people start trying to understand it, and the first, since it's collective, the first model is a hydrodynamical model that people could do with taking into account the neutron excess. And finally, in 1987, there was the first experimental proposal for the J Park, which never really carried out this experiment, but it was the first experimental proposal to look for them in '87. There were already at that time some speculations what it would be. It would be like a soft excitation at very low energies due to this neutron excess. And you can make this cartoon picture here similar to what we do for giant resonances of a neutron background oscillating against a tighter core. It would be similar to what we understand for giant resonances on a smaller scale with the smaller strength. So these are the hydrodynamical models which exist for a long time. And the way you solve this problem is, of course, you mount a Hamiltonian, you have a kinetic energy, and you have a potential energy. And this potential energy is due to the difference in density of protons and neutrons. And there are ways to think about what these collective excitations would be in a gamma of, not a gamma of Gold-Haber-Teller model, or in a Stein-Vedel-Jensen mode of oscillation of protons against neutrons. This is not charge, it's just neutrons and protons, just to give an idea of what is intended to do in these hydrodynamic models. So in the 80s already, but also here in these papers, people had done hydrodynamical models to describe Pygmy resonances, and what they were driven to this physics by the experimentalists like Tanihata and Bjorn Jonsson, who in the 80s, they were discussing a lot about halo nuclei and neutron-rich nuclei, but mostly light nuclei. But they were already thinking that one could describe such nuclei in terms of collective excitations, and in particular these Pygmy resonances. And if you follow the playbook in textbooks about how to calculate transition densities, like this one plotted here, published in this paper here, and try to make rough estimates of what is the restoring force and the bulk of the inertia, you come up with numbers which make sense for this energies and width of these states. And then there were also some wild ideas about what would happen if these Pygmy resonances really existed. For example, we could change the relative abundance of elements when you look in the along the nuclear charge, because these Pygmy resonances would absorb energy from the medium in a cataclysmic event, and this would change the abundance, how energy is going from one nucleus to the other and powering nucleosynthesis. Okay, so what can we do on Earth? So we are very limited in what we can do in a nuclear physics laboratory. Nuclei are not like neutron stars. And we can do things like Coulomb excitation. This is a typical thing that people were doing in the 80s and people do up to now. What you measure there is the nuclear response to a certain operator, and you have in order to reproduce experimental data, you have to make a theory for the wave functions, initial and final states. And if you think about what you put in these wave functions in the continuous and in bound states, you come up with some predictions for what would be the energy for example, what I have done here with Andrew Sustich. And so, for example, for beryllium-11, which is not proper to think about collective models for this sort of nuclei, but people are thinking, could this peak here be Pygmy? In fact, if you look at papers in the 90s, there is a lot of people who discuss, no, this is a resonance because it's a peak. But of course, you can show that phase space kills the response here, and the energy limit of the hard photons or virtual photons also kills here. So whatever you have in the middle has to be a peak, not necessarily a Pygmy resonance. So there was a lot of discussion about this in the 90s. And also at that time, there were lots of colleagues doing three-body models for nuclei such as lithium-11, and try also to understand if this would be some sort of soft state or just due to phase space and energy limitations of the virtual or real photon that was being used in the experiments. So people came out with some formulas trying to fit the data, and then they realized things could get very complicated because of finite state interaction and so on. Then there was a field also of a halo effective field theory, which was developed in the 2000s, in which people were trying to understand phenomena involving light nuclei by using the traditional quantum field theory approach, which is very different than what we do in traditional nuclear physics. So in the Schrödinger equation, here they calculate all things associated with the quantum field theory, Feynman diagrams, renormalization, regularization, and so on. But the idea is to have something which would be more accurate than because you have some control on your and as you know, nowadays effective field theory is largely used in nuclear physics as a way to connect to the short-range physics. So here you see a peak again for this system. Whatever you do, you find these peaks. Of course, they are related to phase space and a response which does not necessarily relate to a Pygmy resonance. More recently, for example, Daniel Phillips has worked a lot on this, and this is again the same thing, experimental data, response, and you see a peak there. Well, it evolved. For example, with Sustich, we had observed that if you do a continuous RPA calculation, you really have, because of the low binding, a peak at low energies, which does not have to do with a collective excitation, but more with single particle excitations at low energy, just because of the low binding of these systems here. And while all the rest, like in the core, the response should be like it is for most nuclei. We also had done at the 90s some models, including some correlations, and we also have observed that what people were doing with two-body, three-body models trying to reproduce the data was fortuitous. It was sometimes something because it was working well because it was not complicated. If you complicate, if you put finite state interactions and correlations, things get broader and deviate from experimental data. So people have also, when they went to heavier nuclei, the traditional model to tackle this sort of problems is to use density functional models. And here is the playbook for Hartree-Fock calculations. The good thing about this is that you get directly from these calculations the energy density functional, which gives the energy as a function of the density, which you can easily relate to neutron stars. You include pairing in these calculations either through perturbation like a BCS model, or you go more precise with the Hartree-Fock Bogoliubov. You still introduce other things like the pairing interaction and some extra parameters with pairing, which could be volume pairing, surface pairing, mixed pairing, and so on. You also, for odd nuclei, you have to, when you calculate, you have to follow some blocking procedure. You put some nucleons in some shells close to the Fermi energy or orbitals close to the Fermi energy, and you make some assumptions, look for the minimum of this system, and that is a more complicated approach than even nuclei. And you can reproduce well. This is something that I participated in my colleagues when I was working with them in the UNDEF collaboration. You can reproduce bulk properties like masses, a large number of masses with this mean field calculation is very powerful. You can also calculate things like that, the staggering pairing gaps, and compare to experimental data, and you see it reproduces data quite well for example, a long isotopic chain like tin. There are problems there. You would need to do some, introduce, for example, in QRPA, you have to introduce rearrangement terms, which this makes some change in the sum rules that you get. Okay, calculations without rearrangement terms. This was one of the things I did with Paulo Avogadro. Lead to higher centroids, and so these are corrections that are necessary in order to be more accurate with these calculations. We have looked for a myriad of experiments that have been done, for example, for monopole excitation and compared to data. Okay, with Sagawa-san, we have looked for these pairing gaps and the comparison to experimental data, and we found that by playing, of course, with the parameters of the pairing interaction, we could achieve high level of accuracy. Also, we could reproduce data. This is not theory. This is just a fit, this solid curve, quite well, and I'll give you an example later. Okay, but how does it connect to neutron stars? As we have seen before, the solutions that we need to, the equations that we need to reproduce mass versus radius in neutron stars, they are very simple. This is the Stoff equation, which is not much more complicated than what we do for the sun. And here we need the pressure as a function of density. And this comes, if you would have the energy as a function of density, you just take some derivative and you would have to, this is the equation of state that you need to solve this Stoff equation. Now, traditional approach is to take the energy per nucleon and expand it around the saturation density. And for example, the first term which will come out is second power of the difference between the density and the saturation density. And this is the incompressibility of nuclear matter. And if you have that, you already can plot figures like this: the mass of a neutron star times its radius. This is something that we have seen repeatedly in this meeting. And now you can go beyond, and you can also look for the difference between protons and neutrons. And so this is called the symmetry energy term of the equation of state. And even the symmetry term of this, this is the symmetry term, and even this coefficient here in front, you can also expand in terms of the difference between the density and the saturation density. So this is the usual form that we use to relate this symmetry energy term to the deviation from the saturation density. And this L here is much into dispute today. This is this low parameter of the symmetry energy, which is the derivative of this quantity with respect to the density. And as you see here from a table from some of the SCRM results, we get more or less the same for the compressibility of nuclear matter. We get the same, more or less the same for the bulk volume term of the symmetry energy. However, for the slope parameter, we can get values which in fact can range from 40 to 120 MeV, depending on the SCRM or the density functional that you take. Now, to increase this problem, we have that to make the problem even more important, how to fix L, as we have seen before, the pressure in neutron stars, in pure neutron matter, if you assume there is one proton and 200 neutrons in neutron stars, so basically it's all neutrons, is directly related to this coefficient here. That's what we can measure in a laboratory on Earth. So this is what we expect for the equation of state of symmetric nuclear matter. Neutron stars are more or less close to this pure neutron matter equation of state. So it's very different than what we can measure in the laboratory. There are problems also even for symmetric nuclear matter. We see here that this is a typical plot. For example, Alex Brown and others have, and many others, in fact, have propagated this idea that you can fit everything here with all the tools we have in density functionals. But when you go away from the saturation density, all these different functionals, they deviate from each other. So meaning that it's very hard to make a prediction for neutron stars coming from it. There are other approaches. For example, some people are using tools associated with the effective field theories, Cairo effective field theories, and so on, to try to make this extrapolation better, okay, and to try to constrain the equation of state as we come close to the neutron matter. So this is a cartoon I took from a paper I wrote with Zelevinsky just to talk about another paper. And this is really what we can do on Earth. Here you have the neutron skin, which is very small, right? And we want to reproduce from observation of the neutron skin 10 to the 57 neutrons in a neutron star. So it's a hard extrapolation when you think that you have to go from 1 to 10 to 57. Okay, so there are many colleagues of us, Fernstow and others, who have shown this before, that there is a correlation between the neutron skin and this slope parameter. When you calculate different functionals, even with a relativistic mean field, you obtain a straight correlation between what is L and what is this skin here. So if you could measure the skin, we could constrain better the functionals which would reproduce that data, and at that as a byproduct would also obtain this slope parameter, constraint on the slope parameter. So that's the idea that has been discussed before. What we know about neutron skin measurements, not much. We have antiprotonic atoms, data from antiprotonic atoms, and you see that the data is very scattered. And for example, anybody doing mean field can reproduce this data because the error bars are so large. So here we have the experiment, and here we have some calculations using different sorts of pairing, and we go through the data, but it doesn't mean much because of the spread of the experimental data. So we really need to do something extra. And that's why there is this experiment proposed and has already been done, and there is following experiments which try to use this parity violation in electron scattering. And here is a cartoon from our chair showing that there is a correlation between this term and the neutron skin. So we could constrain what would be the best functionals to reproduce the experimental data for neutron skin, and from there you could go to the stars, to neutron stars. Another way to look for it is, again, doing Coulomb excitation. You can obtain the cross-section for it is something which is the cross-section for a real photon, but there is this energy in the denominator. And Jorge has shown in a previous paper that this is a good probe, because if you had a Pygmy resonance here, you could enhance the observation of the Pygmy resonance by looking at the response, the integrand of this here through the dipole polarizability. And in fact, people have observed that. You see that this is the response at low energies that comes through the fact that in these experiments you enhance the low energy part of your measurement. So there is also a correlation between this quantity, the dipole polarizability, and And the neutron skin, this has been discussed by many, for example, P.G. Reinhardt or Vitek Nazarevics. They have discussed this to exhaustion. And some experimentalists have measured by using this correlation between dipole polarizability and neutron skin, they have constrained a value for what should be the neutron skin in this nucleus here. Of course, the error bars are also large. I don't show them here. And this is not, this is in accordance with some of the calculations that we have. But if you look for this correlation again, and if you put here the different results from the functionals, you see a sort of spread. And what Rocamassa proposed with NewsPar was that, in fact, you have to multiply by the volume part of the symmetry energy, and then the correlation, you go from here to here, becomes much better. This is a plot I took from a recent paper I did with Tom Allman. So here is the results from different experiments on the alpha polarizability as a function of time and of experiments and of calculations for calcium-48. This is reported in this paper here. You see that we are still trying to decrease or increase the accuracy of these experiments and take a relation between them. There are some problems with the reaction theory. We, for example, try with the reaction theory to mean field calculations, time-dependent mean field calculations. These are very costly. And Oral Bulgak has developed a wonderful tool in order to do time-dependent Hadrifok-Bogoliubov calculation, of what he prefers to call superfluid local density approximation. And there you can also try to connect to the Pygmy resonances. I'm going a little bit fast now because my time is running out. We have proposed recently in this paper here, in collaboration with my colleagues in GSI, that we can look, there are not many things we can do in experiment on NERS, okay? So you have a beam and you have a target, okay? And that's what you have to live with. We don't have neutron stars to do in the lab. So we have to do crazy things like that. Look for a fragmentation reaction and see if you can handle, by looking at the probabilities of removing neutrons or protons from nuclei, there is a direct connection to the densities, the neutron proton densities. And from there, you could try to make, by looking at different predictions for the skin from different functionals, density functionals, we could connect to the experimental data that's yet to come. This has been approved for an experiment at the GSI, and to connect to what are the best functionals to explain the data, and by default connecting to this log parameter. So here you see that the skin for thin isotopes with different, these are different, each of these dots are different SCRM functionals. And this is Hadrifok-Bogoliubov calculations. And you see that, in fact, there is a spread of the skin as you move along the isotopic chain. And it's not as beautiful as we have seen those correlations, but you see here that the neutron skin also correlates with the slope parameter for different functionals, okay, along the isotopic chain. If you look for medium heavy nuclei and a heavy nucleus, medium heavy nuclei and heavy nuclei, you see that these fragmentation reactions, they behave differently. This can be exploited, for example, by using proton targets or carbon targets and trying to find out. This has not been done. This is just a proposal. And more recently, I have seen this on physical review letters like a week ago. Some of our colleagues in China have also proposed to look for particle production in relativistic heavy ions and try to find out a connection to the neutron skin. So I think I am on time. I just want to talk about a little thing. How much time do I have, Xavier? 0.
Yeah, I'm here. So you have, let me check. Yeah, you can have 7 minutes.
3 minutes.
Well, no, sorry. If you want, yeah, you are right. We need to leave some time for questions.
Yeah.
So yeah, let's say 3
So
minutes.
we have also proposed something together with our colleagues in Germany, is to go back to this very old physics, which is associated with the scattering of polarized protons. So the idea in this cartoon, very schematic cartoon, if the proton hits the other proton here in P2P reactions, okay, on this near side and on the far side, and of course this is a quantum mechanical system, so part of the proton goes through here and part of the proton goes through here, and there are interferences, right? So that's how we see the wave mechanics of scattering and inelastic scattering too. So the only thing is that the spin orbit term changes in going from this side and in going from that side. This has as a consequence that also when you look at the nucleon-nucleon interaction, they are different for singlet and triplet states. And the difference gets amplified by this state and also by the absorption and the distortion of the wave functions, the scattering wave functions as they go through this side and this side because of the length of the path, right? So we have resurrected this, which is beautiful, this effect. In fact, it's P2P reactions. You see here is a symmetry term that we have to look for. This is the difference between proton up and proton down scattering. And you see that there is a big difference for one orbital, the P1/2 and P3/2, for example, for this reaction here, 200 MeV. And this dates back to this Maris in 1979. So if we could do this in the laboratory, and that comes the problem with the radioactive beams because of their intensities, if you could measure this asymmetry as a function of the neutron excess in nuclei, we could perhaps get good results because theory predicts the change is relatively large. And as if you want to see in terms of the radius, the skin, you see that as the skin increases, this increases by a reasonable amount that we can do in experiments. This has not been done, it's just some idea. Okay, so here is my summary. I think that we started to look at light nuclei with halos, and people at that time were already talking about a so-called Pygmy resonance, and how does it relate to the bulk properties of nuclei. Then more recently, we start talking also about the skins in nuclei and adding to the Pygmy and thinking that they have a nearly linear correlation, trying to extract from these two sorts of measurements, skins and Pygmy excitation, something which could connect to the neutron stars. There are some things that have not been done, and even the skin in the Prax experiment in Jefferson lab, the results are limited in accuracy, and we are still fighting to see if we can connect this and have other ideas to get to the slope parameter of the symmetry energy. So I think there is still a long way to go, and there is a lot of opportunities for young scientists to get involved with it. And I hope that some of you will be interested in this subject and perform some experiments in ITHEMBA labs, a wonderful lab in Cape Town and all around the world too. Thank you.
Thank you very much, Carlos, for the very nice and clear talk. So we have a question from Jorge. So Jorge, please go ahead.
Yes, thank you, Carlos. So I just want to mention something because you provided a theoretical result from the scheme from EFT calculations about 0.17 Fermis for the neutron skin. I'm not sure, you probably already know that T-Rex came back and did the experiment again, and they reported a number of 0.29. Yeah, plus or minus 0.07. So I would say that the tension continues because 0.29, even with 0.07, is really pushing it. in the sense that there is definitely some tension that has to be resolved. So Pyrrhic, yes, so our colleagues in Jefferson Lab have worked very hard. They reduced the error bar by a factor of 3, but the large value for the scheme still remains.
So I have a question for you, George. How about this CRESS experiment? Are you talking about the CRESS or
No. This is LED 208. This is Pyrrhic 2.
Okay.
Yes, the second
But
version of
the CRESS experiment didn't perform yet, right?
the CREX experiment on calcium 38, yes, it had finished, but the analysis will take about 10 months. But it's
okay. Okay, so there are some. So what you're saying is that this number 0.17 with the new measurements changed to 0.29.
No, yeah, but this number that you're quoting, this is a theoretical number, right? 0.17.
Yeah, I know. So you are talking about this number. Yeah.
No, I'm talking about two things. So you extract the neutron scheme from here. The only thing that I want to say is that the experiment that used the parity violin experiment obtained 0.29 plus or minus 0.07 Fermi.
Okay, I got it.
Okay, is that number published?
So the paper is being written, but there was a recent meeting of the Division of Nuclear Physics of the American Physical Society, and the number has been officially released.
Okay, good. Thank you.
You're welcome. Welcome.
So if there are other questions, please, you can go ahead. I don't see any raised hands. Let me check the, okay. So no other questions. I have a question myself. So Carlos, I missed some, when you were talking about the Pygmy, I was very excited and I wanted maybe some conclusion at the end, right? So kind of, so to me, the Pygmy is this or is that. So, but you didn't, let's say, give any kind of conclusion on the Pygmy, let's say, section. So was that on purpose or?
Yeah, well, it's because I do not know. I have been in a meeting in South Africa, in fact, 2 years ago, I think. And there was a whole session one day dedicated to that. Maybe you were not there, Xavier?
No, I was not there.
You were not there. Well, there is a discussion if this strength which is observed at low energies, if it's really collective or if it's really just isolated single particle excitation, so which pile up close to threshold. Something similar to what I have discussed in terms of light halo breakup, and it could, for a heavier nuclei, be something like that, which is not really a collective state. So I have the impression that from the experimental data that we have, it's not easy to say by comparing to theories if this strength that has been observed at low energies is really what we think is a collective state. And some of my colleagues in theory say it doesn't really matter. Okay, what you need is to reproduce the experimental data, and whatever you use to reproduce the experimental data would have inputs which connect, for example, with this low parameter, and that's what you need.
Okay, thank you very much. There is a question from Philip Atley. Philip, you can ask it yourself if you like.
Oh, okay, thanks. I was wondering about the knockout results that you, or the knockout idea that you showed, the P2P. Does this require that there's the spin orbit partners like the P3 halves, P1 half? And
you have to have spin orbit partners. That's the idea here, because
okay, so
I'm sorry, go ahead.
At 10, you've got like the G9 halves and the G7 halves, but I think they're on either side of z equals 50, right?
Right.
So does that limit where you can use this to look?
No, it doesn't. If you have different occupation numbers, it comes all from the different singlet and triplet flat scattering, which is amplified if you have different numbers. Okay, so if you have different numbers, then this Maris effect is amplified based on the rotation of the orbit. So you could also do this for the g orbitals if they are differently populated.
Okay.
This is a difficult experiment. Some Japanese have done this experiment. In fact, the outcome is not great. That's why we should go and try to see if we can do better. But these polarized scattering things are very complicated, technically, from the experimental point of view.
Yes, and I seem to recall some of the carbon-12 P2P results from RCMP show strange effects in the population of excited states and things. So they might not be. There might be some strange reaction theory things going on as well.
Yeah, there is a lot of problems in nuclear reaction theory, and we have to fix these problems because we want to extract information about the nuclei, and we need to have good reaction theory. And the reaction theory at very high energies is complicated. There is no really path to do an ab initio approach as you have at low energies, where you could use some sort of ab initio method, let's say. At high energies, everything is short range. You know, you have these nucleons scattering at very hard collisions. So there is the separation of scales, which is used in low energy physics, in structure and low energy scattering, is completely different and disallowed when you do high energy scattering, excitation, knockout, and things like that. So it's very, it still has a lot of problems, and we have to fix these problems. Otherwise, what we extract from nuclear structure is not, it can be questioned, you know.
Okay. Thank you very much, Carlos, for this answer, very complete answer. I don't know if there is other questions. Please, if there is other questions, go ahead. Otherwise, I think there is, it is, let's say, time to close the last session and to thank all the speakers and Carlos.